Hi everyone, welcome to my video on the time domain analysis on the closed loop systems. So in this video, I'm going to talk about the transient analysis, and basically what you see here is that there are three types of systems. The A will be the first order system, B will be second order systems with the overdamped response, and part C will be the second order system with the underdamped response. So in this video, for the sake of the brevity, I'm going to skip all this proving and concept, and I'm going to directly to use the final solutions or the final answer template just for the sake of the applying the solutions onto different type of problems, and then to get the output as quick as possible. So the solutions here will be break into three parts according to a different systems. Okay, so the first one that we will be looking at will be the first order system. So first order systems, basically we are going to cast the transfer function into a standard format of k over tau s plus 1. But we are not going to use the forward transfer function, but rather we are going to use the closed loop transfer function Ts equals to k over tau s plus 1, where k can be any arbitrary number, while tau will be the time constant of the system that will be critically related to the settling time and also the rise time of the system. If the system is without any zero, then the first order system will not exhibit any overshoot. So let's work out this Ts. Okay, so our Ts will be equals to G over 1 plus GH, which means 0.5 over S plus 2 divided by 1 plus 0.5 over S plus 2, which will finally lead us to 0.5 over S plus 2.5. So in this case here, the tau and also the k can be determined by dividing both numerator and denominator with 2.5. So 1 over 2.5 s plus 1. And then the important one will be our tau, which will be 1 over 2.5, which is equals to 0.4. And from here, we can determine that the settling time and rise time, we can approximate settling time to be approximately 4 tau. So we can get approximately 1.6 seconds. And then our rise time can be approximated as 2.2 tau, which we can approximate to 0.86 seconds. So this will be our working. And to see whether the approximation is accurate or not, let's simulate it inside the MATLAB. So using MATLAB, we first define the transfer function g according to what we have, and we use the feedback function to actually find out what will be our t. And finally, we can actually get the simulation output by using step function. So the step function here accepts a unit step input and produce the output as shown in the graph. So from here we can see that our approximation is actually quite accurate. Okay, so let's move on to the second one. So let's get rid of everything here. Okay, so the second one will be part B, GS equals to 4S S plus 5, and this is overdamped system. So how do we identify whether the system is underdamped or overdamped? We have to look at the zeta value. So to get the zeta value and also the omega value, we have to cast this GS into TS by using TS equals to G over 1 plus GH. And finally, we cast the Ts into our standard second order form. So first, we find out what will be our Ts, which is equals to Gs over 1 plus GHS. So for the brevity of this video, the final outcome will be S squared plus 5S plus 4. which we can cast it to our standard format, k omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So from here, by comparing the coefficients of this and this, as well as this term and 5, we can actually get the zeta value to be larger than 1. So this means that the system is actually overdamped. So overdamped system has a response of very similar to first order response. Hence, we will use the first order solution template to get the settling time and rise time. So similar to the first order response, my maximum overshoot will be automatically 0%. So from here, in order for us to get the settling time and rise time value, so we have to get the dominant roots value. So the dominant roots value can be obtained by getting the closed loop poles of the system. So which means that we want to get this term closed loop and we equate it to 0, and we will get s plus 1, s plus 4. So based on the magnitude of the roots, we can identify that this is our dominant poles. Magnitude is the lowest one, and we can determine that this is the dominant. So the dominant roots will be the one controlling the system's transient because it stays in the system longer, and s plus 1 so this implies that my tau is equals to 1. So the settling time again can be approximated to 4 tau, which means it's approximately 4 seconds, and rise time will be about 2.2 tau, which is about 2.2 seconds. But this it will not be a very good approximation, simply because if you check back the dominant roots and the non-dominant roots, we can find out that the magnitude is actually quite close, 1 and 4. So ideally, if you want to make sure that the dominant roots will control the system and behave as a first order, we have to make sure that the magnitude between the dominant and non-dominant will be separated to at least 10 times. So in this example, these two are not separated large enough. So whatever that we get here might be just somehow a mediocre approximations. So let's check it out using simulations. So using the similar manner but slightly different transfer function mode. So we use the zero pole gain here. So we find out the G, and next we find out the T, and finally we simulate the step response. So our approximation method here still works pretty much good if you think if you can accept a small tolerance in this the difference between the our answers and also the answers showing in the MATLAB. So we'll consider it solved as for this moment of time. So if in a later stage, okay, so if you have time, then we'll discuss more on how do we get more accurate approximations of the second order overdamped, provided that the roots are not, the dominant roots are not separated in a very large ratio. Okay, so let's move on to part C. Okay, again, let's delete everything here. Okay, so it's clean now. So let's look at the third example, part C, where we have this second order underdamped system. So similar manner, okay, how do we identify whether is it underdamped or overdamped? We check the transfer function of the closed loop systems. So we have a GS over 1 plus GHS, and then at the end we have 1 over S squared plus S plus 1. So by comparing this with the standard form, omega n squared, S squared plus 2 zeta omega n S plus omega n squared, we will have the omega n will be equals to 1 and our zeta value will be 0.5. And because the magnitude is less than 1, hence the system is underdamped. So for underdamped, we are going to use a set of formula that actually calculates what will be the maximum overshoot, settling time, and rise time. So let's look at the settling time first. So settling time will be equals to 4 over zeta omega n, considering the 2% criterion. So we will have 0.5 times 1, we have 8 seconds. So maximum overshoot will be exponential, negative zeta pi divided by square root of 1 minus zeta square, multiply 100%, and we have 16.3%. So as for the rise time, we have to calculate the beta value and omega d. So beta will be inverse tangent of square root of 1 minus zeta square divided by zeta. So we will get approximately 1.047, and omega d will be equal to omega n square root of 1 minus zeta square. We have 0.866. So our rise time will be pi minus beta divided by omega d, and at the end we are going to get about 2.419. Let's check out the solution, okay, whether is it accurate or not using simulation. So similar to part B, almost exact code that we are using except for the transfer function, we can get the output, and as you can see here, our calculations here are confirmed. So but one thing we have to take note is that MATLAB is showing the rise time using the criteria from 10% to 90%, but the solutions that we are actually using here is actually benchmarked against the calculation using 0 to 100%. So of course, using the simulation result from MATLAB, we are going to see a difference, and hence if we want to verify our solution, we have to choose the point where the system hits 100% at its first time. So in this case here, we can see that our solution here is actually matching with the simulation result. Okay, so that's all that I want to show in this video. Hope you all can learn something. Okay, so in the next video, I'm going to show how do we analyze the steady state and also the stability of the closed loop systems. So thank you for watching. Bye.